All right, guys, part 2 of this lab. What I'd like to be able to do is to figure out what the heat of fusion of ice is. So I've got some ice here, and that ice is going to melt. And when it melts, it's going to take a certain amount of energy for it to do so. Now, how are we going to figure that out? Well, we're going to, again, use some calorimetry. So we're going to start here with some water. And again, I'm going to start with 100 milliliters of water, which is going to be, again, 100 grams. And I'm going to put it in there like so. So it is in my calorimeter. And I'm going to take its initial temperature so that I know where that water is starting. And then what I'm going to do is I'm going to start adding ice into this guy. And the ice is going to melt. And as the ice melts, the temperature of the water is going to decrease until it gets down to 0 degrees Celsius, at which point I know that we are about done. And again, you should get to exactly 100 degrees Celsius, or 0 degrees Celsius. We might not exactly get there, but we'll see what happens. All right, so we're going to start here once again at 25 according to this thermometer. So we're starting at 25 degrees Celsius. So now what I'm going to do is I'm going to take a couple pieces of ice that are here. So I'm going to take this, I'm going to put that in, and I'm going to put in some ice. Like so. And at this point, what I'm going to do is I'm going to put on the lid and I'm going to stir, stir, stir. And I'm going to stir, stir, stir until all of the ice is melted. So I'll come back when all the ice is melted. So I have skipped the boring part of this, and I have now put in enough ice that it has melted, and it's gotten darn near 0 degrees Celsius here. So if all the ice is melted, and I am at about 3 degrees Celsius. Now, technically speaking, I should be at 0 degrees Celsius here, because any difference between the 0 and like the 3, for example, is going to be a source of error, because I'm not going to account for that change in the temperature. So I should be all the way down to 0, but I'm not, because this is a quick rough experiment that's here. So I've gotten all the way down to 3 degrees Celsius. So again, I started at 25 and I ended over here at 3. Now you might be thinking to yourself, but in order to know this, I need to know what the mass of the ice is, and I didn't do that before the experiment. Why not? Well, if you put the ice on the scale beforehand, then what that means is that you're going to lose some of the energy as the ice sits in the scale. Plus, we have kind of a elegant end around the problem. Remember, we started with 100 milliliters of this, right? Now that I put ice into it, I'm going to have more than 100 milliliters. However much more than 100 milliliters I have is going to be how many milliliters of water were added from the ice. And if I know then the milliliters of water that were added from the ice, I know the grams, and so then I can figure out the grams of the ice. So all I have to do is to take this guy and pour out 100 milliliters. And as soon as I pour out 100 milliliters, there we go, that's pretty darn close to 100 milliliters. So there is 100 milliliters that is gone. Whatever is still left in here is how many grams of ice that I put in, because the density of water is 1. So by the time we were all said and done, it looks to be like we are at, right at around 32 milliliters. So that means I must have added about 32 grams worth of ice to this. So 32 grams of ice were added to 100 grams of water at 25 degrees Celsius, and it ended up down at 3 degrees Celsius. Using that information, we should now be able to figure out what the specific, or the latent heat of fusion is of the ice. Let's do some calculations for this. Now we have a very similar situation to our specific heat of the metal circumstance, except that the roles are a little bit reversed here. So what's going to happen here is that the heat actually is going to go from the water into the ice, because the ice has to get melted. So the water is actually exothermic in this case, because the water is going to get cold, and then the ice over here is endothermic, because the ice is what is absorbing the energy in order to then melt. So the water is actually exothermic in this case, where it was actually endothermic in the previous case. So what we've got here is we've got our basic equation, which is that Q lost is going to be equal to the negative Q gained that is here. And the Q that is being lost here is being lost by the water, and the Q that's being gained is that which is by the ice that is here. All right, so the water is just cooling down. So the liquid water is not changing any phase. And so consequently, the Q equation for that is going to be MC TF minus TI for the water that's there. But the ice is actually melting. And because the ice is melting, then what we're going to do is we are going to do the phase change equation for that, which is not MC delta T, it's actually M times L. Don't forget our negative sign that's here, got to include that. So this is going to be the M, and this is times the L of F of the ice that is there. So our equation is MC TF minus TI for the water, and then that's going to be equal to M times L of F of the ice. And what we're doing is we're looking for that number right here. We are looking for the heat of fusion of ice, which means that we need to know all of these other numbers here, and we've got all of those. So if we check our data table on the next page, we started here with 100 grams of the water. And we know that the specific heat capacity of water is 4.2. And then we know that the water started at 25 and ended at 3 there. So we can figure out what water is. So we can come up here and we can say that water is going to be 100 grams times 4.2 joules per gram degree Celsius times 3 minus 25 degrees Celsius for the water. And then, as far as the ice is concerned, we got to have the negative. And then don't forget that what happened in there is that we had 32 extra milliliters of water after we were done, because we started with 100 milliliters and ended with 132 milliliters. So we had 32 extra milliliters of water, which means that we must have had 32 grams of ice in there. So our ice was 32 grams, and then L of F is what we are looking for. That is our X. Now, quick reminder, we are cheating a bit here because we're supposed to get all the way down to 0 and we didn't. Why does that matter? Because technically speaking, then the ice not only went from solid to liquid phase, but it also warmed up by 3 degrees Celsius. So if this was going to be perfectly accurate, we should have gotten all the way down, added enough ice to get all the way down to 0 degrees Celsius. But we're just going to get close. This is pretty good, and it's going to be a source of error that is involved there. So just keep in mind that is going to be a source of error. So I got 100 grams at 4.2 at negative 22. That's going to be negative 9240 over here, and then that's going to be equal to negative 32 times x, because that's what we are looking for. So divide by negative 32, divide by negative 32, and we get an answer of about 289, and that's in joules per gram once all of the units cancel out. Just for comparative purposes, the actual correct number is 333 joules per gram. So we got pretty close, actually. So 333 at 289 divided by the 333. We got only a 13% error. So we got a 13% error for a very quick and easy calculation here. Had we again taken a little bit more time, made sure we had enough ice to get all the way down to 0 degrees Celsius, we would have gotten a little bit more accurate there. Not to mention the fact that we are ignoring any heat loss to the environment. We are ignoring any heat loss to the styrofoam container itself. So this is riddled with little sources of error that add up here and there, but the basic bones of what we are talking about here is actually pretty accurate there. So we got a 289, it was supposed to be 333. That's pretty close.